we're going to look at the chapter 22 problems. We've been shooting these vertically, the idea being that if you're viewing the video vertically, you have more space to have the overheads open at the side or solutions. So in case you can't see this very well, you can hopefully have it also open at the side. You have these solutions, so it should be no problem. In the previous video, I'd mentioned about the damn interesting article, and if you look at home viewing here, I was right. I've given you a link to the damn interesting article about FM radio, which is a really good article, I think, so try to watch that. We also have Maxwell's equations here, which you should have watched anyway because it was on the schedule to watch. Okay, let's take a look at these questions. The first few are a little bit esoteric in a way, but we'll work through them. And then sort of the latter ones are a bit more practical. So say the first ones are a bit, in a way, a bit contrived, the questions. Okay, question 1. Determine the rate at which the electric field changes between the round plates of a capacitor, 8 centimeters in diameter, if the plates are spaced 1.1 millimeter apart and the voltage across them is charging at a rate of 120 volts per second. Well, the electric field is the voltage divided by the distance, right? We want the rate at which the electric field changes, so I'm going to differentiate this equation. The plate separation of the capacitor is constant, so that comes out in front of the differential. And then dV dt is given at 120 volts per second, and there I plug in the numbers and out pops the answer. Easy enough, okay? Question 2. At a given instant, a 3.8 amp current flows in the wires connected to a parallel plate capacitor. What is the rate at which the electric field is changing between the plates if the square plates are 1.60 centimeters on a side? Okay. So what I want the electric field is changing. Let's think for the capacitor, or a parallel plate capacitor, CV equals Q. For a parallel plate capacitor, the capacitance is given by epsilon 0 A over D. We actually proved this using Gauss's law earlier in the course. What I'm going to do here at this step, I just put this V over D here, because V over D is E, right? So I can think epsilon 0 A E equals Q. If I differentiate both sides of that equation, I've got my constants epsilon 0 A, dE dt equals dq over dt, which is I, and then I've got dE dt is I over epsilon 0 A, and I think that's what I want, isn't it? Right? So the rate at which the electric field changes, I've got the current, I've got epsilon 0, I know the area of the plates. Be a bit careful with the unit conversions, throw the numbers in, and out pops the answer. Okay? Question 3, a 1500 nanofarad capacitor with circular plates 2 centimeters in diameter is accumulating charge at a given rate at some instant in time. What will be the induced magnetic field strength 10 centimeters radially outward from the center of their plates? What will be the value of the field strength after the capacitor is fully charged? Okay, I've given you if you look below the question, I've actually given you Ampere's law, but with the extra term that Maxwell added. Here it is here on solutions. For the parallel plate capacitor, again we have CV equals Q, and the capacitance of the parallel plate capacitor is epsilon 0 A over D equals Q, EA equals Q over epsilon 0. Okay, so that would be the flux, right? That would be the electric flux in the capacitor. The integral around a closed loop of B dot dl equals mu naught I. Now, in this case, because our loop is around the capacitor, there is no current, so that term is 0. We've then got epsilon 0 mu 0 d phi dt, where phi is the electric flux, and the electric flux is given by Q over epsilon 0. So if I put that in, you can see that the epsilon zeros cancel out, and that gives me 2 pi r b equals mu 0 dq dt, and I'm told what dq dt is. There it is there, and I then just have to put my value for mu0 in, and b, I guess I've divided by 2 pi r down there, and out pops the answer. In a way, this is, as I say, these questions are a bit contrived because this is the current, isn't it? 32 coulombs per second is 32 milliamps. And so what I could have done in this question is drawn my Amperian loop, and then instead of the loop being between the plates of the capacitor, I could have stretched it around such that the current pierced it, and then it would be the same. You can see, if you think about it, it really is the same as if we'd done that, because all we're saying is integral of b dot dl equals mu naught I. That's what it boils down to, right? So we do it in this very convoluted way, but in a way it would be a lot simpler. The second part of the question, what will be the value of the field strength after the capacitor is fully charged? After the capacitor is charged, the electric field is not changing between its plates, hence the magnetic field will be 0. If the electric field is not changing, no charge is flowing, there's no charge in, no current in the wires. Okay. Okay, question 4. Show that epsilon 1 over that is the speed of light. I claim that Maxwell's theory gave us that as the speed of light, so dimensionally that should come out as a speed. This is a question I could have given you in Physics 1143, even if you don't really know what these things are, if I gave you some equations. So what we need to do is sort of to beat through things and work out the units of epsilon 0 and mu 0, and doing that we can then substitute in, and hopefully everything cancels down. Well, here is Coulomb's law here with the epsilon 0. Rearranging here, there's epsilon 0, so I can see that the dimensions of epsilon 0 are Coulomb squared, Newton meter squared. Now, if I want to get this into base SI units, because it's probably easy to work in base SI units, I can multiply it by 1, second squared over second squared. Coulomb squared over second squared is amp squared, so that gives me amp squared, second squared, Newton meter squared. Okay. For mu 0, we can use Ampere's equation here. There's the extra term, but dimensionally that would have the same units as that, so we can just use this. B, let's get the units of B first. Here's F equals I over B sine theta, so B must have units of Newton amp meters, right? The Tesla, Newton amp meter. Here's the Ampere's law, so dimensionally mu 0 is Tesla meters per amp, and if I put in the units for Tesla here, Newton amp meter over meters amp, these cancel out, so it's newtons per amp squared. Okay. I guess I got newtons in. I'm going to leave newtons in instead of reducing them. If I evaluate this expression here, then there's epsilon 0, there's mu 0. I use newtons, I use amp squared, so it's 1 over the square root of second squared over meter squared, which is 1 over seconds per meter, which is meters per second. Okay. There's probably many ways you can go about that. That's just the first one that came to mind when I was writing the solutions. Okay, question 5. In an electromagnetic wave traveling west, never eat soggy weenus, I guess that way. The B field oscillates up and down vertically and has a frequency of 90 kilohertz and an RMS strength of that. Determine the frequency and RMS strength of the electric field. What is the direction of its oscillations? So we will say that our B field is going that way. It oscillates up and down vertically. The electric field will also be west, but it would oscillate horizontally, right? Because it's always at 90 degrees to the magnetic field. So that's the first part. The frequency would be the same. So it's the same frequency, the same direction, but it's oscillating at right angles, so it's oscillating horizontally instead of up and down. And the RMS field strength, well, remember there's this relationship B times C, BC, easy one to remember, equals E, and I want E, so E will be equal to BC. So hopefully that's kind of what I've said in the solutions. I don't know if north to south really makes sense in that context. I have to think about that. But they're at right angles to the oscillations of the other field, okay? Okay, I think that's easy enough. Okay, question 6. So as the first 5 questions are sort of a bit esoteric. It's like they don't really have many practical applications. These questions, I think, are kind of a bit more straightforward in a way, and shouldn't be as hard or as hard to get your head around. Okay, a light year is a measure of distance, not time. How many meters does light travel in a year? We know the speed of light, so we just have to multiply the speed of light by a year in time, and that will give us a distance. So distance equals the speed of light times time. There's the speed of light. The only catch is we need to get a year into seconds, and we did this in 1143. Here's all our various conversion factors, which changes years into seconds, and then you can see the seconds cancels out. It gives us a distance in meters, about 10 to the 16 meters, which is a long, long way away, right? It's far, far away. Question 7. A spherically spreading electromagnetic wave comes from an 1800 watt source. At a distance of 5 meters, what is the intensity and what is the RMS value of the electric field? Okay, the intensity is equal to the power over the area. So the intensity, which is the power per square meter, I just get the power divided by the area, 4 pi r squared. It's the area of a sphere. So that gives me the intensity at 5.7 watts per meter squared. The intensity is given by 1/2 epsilon 0 c epsilon 0 squared, and epsilon 0 then, solving for epsilon 0, it gives me this, put some numbers in, and I get the answer out. There's the 66 volts per meter. The RMS, that would be equal to epsilon 0 over root 2. So the RMS electric field, 46 volts per meter. Okay, that one's a bit odd. I can't think that you'd ever really do that calculation. Question 8. If the amplitude of the B field of an electromagnetic wave is that value, what is the amplitude of the E field? So again, this comes to BC equals E. E equals B times C. Right, so there we go, E equals B times C. Put the numbers in, there's the magnitude of the electric field. And B, what is the average power transported across unit area by the electromagnetic wave? I just have to use this equation here and get the answer out. Okay, there it is. Question 9. Estimate the average power output of the sun, given that about 1350 watts per square meter reaches the upper atmosphere of the Earth, and I've given you the AU. That AU is the distance between the Earth and the sun, or the average distance at least, okay, which we'll use. So for question 9, I'm given the intensity, and so I want the power. Intensity equals power over area. Power equals area times intensity. If we imagine a sphere around the sun at the distance of the Earth, that sphere would have an area 4 pi r squared, r being the distance in astronomical units. And so putting the values in, we come up with 3.8 times 10 to the 26 watts. That's the luminosity of the sun. Question 10, what size should the solar panel on a satellite orbiting Jupiter be if it is to collect the same amount of radiation from the sun as a 1 square meter solar panel on a satellite orbiting the Earth? And we're given the distance of Jupiter from the sun is 5.2 astronomical units. Well, the radiation is dropping off as a square. So if I'm at a distance of 5.2 AU, the intensity of the radiation at that distance is 1 over 5.2 squared less. So to get the same power, I would have to increase my area by that amount. So the answer is simply 5.2 squared, which is around, I don't know, 27. right, which is around 27. Okay. Interestingly, when they do send sort of probes out into the outer reaches of the solar system, the sun is too weak for solar panels to really work. So often what they do, they use a thermoelectric battery. So you get a lump of plutonium, which is just hot all of the time due to the radioactive decay, and that drives a thermoelectric circuit and produces the power. Okay? Solar panels don't really work very well far out in the solar system. Okay, question 11. Suppose you have a car with a 100 horsepower engine. How large a solar panel would you need to replace the engine with solar power? Yeah, okay, I guess that makes sense. Assume that the solar panels can utilize 20% of the maximum solar energy that reaches the Earth's surface, 1,000 watts per square meter. Okay, so let's say I prime intensity is the power per area, but my intensity here, this is my effective intensity instead of the actual intensity. So my effective intensity, I'm saying, is my actual intensity divided by my efficiency. The area is the power I need over the effective intensity. Well, the power I need is 100 horsepower, that's the power of my car engine, times 746 watts per horsepower. So I've got this in watts, and then my effective intensity is my actual intensity multiplied by my efficiency. So you can see the area comes out to be 373 square meters, right? So you're not going to drive around in your car with a solar panel on the roof. That will not supply sufficient power. That said, an engine produces 100 horsepower, but not all of the time. That's sort of the peak power that an engine produces. Most of the time, you do not need that power. We're on question 12, I believe. Cell phones operate at a frequency of 1.9 gigahertz. What's the wavelength of this radiation? Nice simple question. We know the relationship, the speed of a wave is the frequency times the wavelength. The wavelength is a wave speed over the frequency. It's a electromagnetic wave, so it's the speed of light divided by the frequency. So around 15 centimeters. Okay. So cell phones wavelength is around 15 centimeters. Question 13. The variable capacitor in the tuner of an AM radio has a given capacitance when the radio is tuned to a station at a given frequency. What must the capacitance be for a station at the other end of the dial, 1610 kilohertz? Omega 0 equals 1 over root LC. So look, here's omega 1, and omega 1 is 1 over root LC1. Omega 2 is 1 over root LC2. What I really want out of this is the capacitance at the second frequency. Now what I could do, I guess, I could solve this equation and get the inductance here, and then plug it into that equation and solve it for C2. I'd have to put 2 pi's in. It's messy. Isn't it easier to divide this equation by that equation? If I do that, you can see that the inductance cancels out, and I can just express C2 then as the ratio of the frequencies squared divided by C1. This is omega, which is 2 pi f, but of course I can cancel my 2 pi's out, so it simplifies down to this expression here, and there it is, 292 picofarads. Okay, so a simple question. Try and solve it elegantly, and don't bother working out the inductance. Right, it's easier than that. An FM radio tuning circuit has a fixed capacitance of 810 picofarads. What inductance is needed to tune a station at 88 megahertz? Well, again, this looks like a similar sort of question. Omega equals 1 over root LC. I want L, so I isolate L on the left, solve it algebraically. I'm given a C value, I'm given an F, 2 pi f. When I square my 2 pi, of course, I get 4 pi squared. So just be careful with that, and throw in the numbers, and you get around 4 nanohenries coming out. Question 15. What is the luminiferous ether, and what did the Michelson-Morley experiment demonstrate? I don't think I really discussed this, but the idea in the 19th century is that light is a wave, But waves have to travel in a medium. Sound travels in air. You must have seen the classic experiment where you get a bell in a jar, you pump out the air, and you can't hear the bell anymore. In space, no one hears you scream. So there was this idea that there must be something in which the light waves travel. And so that was the luminiferous ether. The Michelson-Morley experiment, they went to measure the speed of the Earth relative to the luminiferous ether. And the idea is a bit like this. If there's a wave going along in the ocean, I can measure its speed. But if I'm in a boat going along with the wave, I measure a slower speed. If I'm going in the opposite direction to the wave, I would measure the speed of the wave to be greater relative to me. So Michelson and Morley measured the speed of light, but they measured it at different points in the Earth's orbit. The idea being, if we're going in a certain direction at this time of the year, 6 months later, we're moving in the opposite direction in space. So they expected to see our motion relative to the luminiferous ether of this fixed material in which light moves. Did they find it? No. Okay? And really, this is what led to special relativity. The Michelson-Morley experiment showed that the speed of light is fixed regardless of the observer, and Einstein built on this and came up with the special theory of relativity. Interestingly, Maxwell's equations are relativistic, though he didn't sort of realize it at the time, that there was no need to have this luminiferous ether in Maxwell's equations. Okay, can electromagnetic waves travel through a perfect vacuum? No, yes, sorry, electromagnetic waves can. Electromagnetic waves, unlike other waves, do not need a medium to travel in. Space itself, I guess, is the medium, if you like to think about that, but maybe that's a bad thing to say. No, electromagnetic waves can travel through a vacuum. If they couldn't, well, we won't see the sun, there'll be no light hitting us on the Earth, and we won't be here. Okay, can sound waves travel through a vacuum? No, they need air, right? So sound waves travel through air. Before Maxwell, theorists had no way to make electromagnetic waves travel through a vacuum. What modification did Maxwell make to Ampere's law to change this? So people before Maxwell had thought that, well, maybe light from the sun is an electromagnetic wave. But, they had this problem that, well, how can it sustain itself? And really it was Maxwell adding this extra term that the changing electric field produces the magnetic field, right? That extra term he added to Ampere's law, which sort of allowed light to travel through the vacuum. Which type of electromagnetic radiation travels the fastest? Well, in a vacuum, they all travel at the speed of light. Okay? All travel at the equal rate. Interestingly, in materials, you might, if you've done sort of refraction, which we'll do later on, but you might hear these ideas that light doesn't travel as fast in glass. But I've just told you that the speed of light is constant, so how do you reconcile the fact that, some people say, well, light travels more slowly in a material, but I'm saying the speed of light is constant and it's fixed. What happens in a material is that the light is absorbed and re-emitted. You can imagine that if I throw this object to another person, it travels at a certain speed as it goes from me to the other person, right? That would be the speed of light. But if the other person catches it and then throws it on average, the speed will be less because they have to catch it and throw it on again. So that's what happens in a material. The light doesn't really travel more slowly. It's absorbed, re-emitted, absorbed, re-emitted, absorbed, re-emitted. So all of this absorption and re-emission causes it to slow down, to appear to slow down. But the speed of light is still 3 times 10 to the 8 meters per second. As light passes through a material, though, it appears to slow down because it's being absorbed and re-emitted. Usually in class, I get something and we throw it between us, and you can see that if people have to catch it, it doesn't go as fast, it slows it down. I forgot what question we're on now. I'm off topic a bit. Oh, that was question 18. Okay. What did I write for that? All EM waves travel at the same rate in a vacuum. This is not so in materials where different frequencies can travel at different velocities. This is an effect known as dispersion, which we'll get to in a later chapter. Certainly, the rate at which light travels in glass depends upon the frequency. But we'll get to that in a later chapter, so I'll worry about the details there. Okay, question 19. The electric field in an electromagnetic wave traveling north oscillates in an east-west plane. What is the direction of the magnetic field vector in this wave? Well, it's going to be at right angles to that. So if that's north and it's going east-west, the electric field has to go like that. So I guess hopefully I wrote up and down. Yeah, so it's moving up and down. So imagine north, let's say that way's north, and it's going east-west. One's doing that, the other's doing that. So it will be up and down. Question 20, list the following forms of VM radiation in terms of increasing frequency. I've given you scrambled, so here they are, and I want a typical source. So increasing frequency, radio waves have a low frequency, okay, which seems surprising because you think of them as high frequency, but X-rays have stupidly high frequencies and very short wavelengths. So radio waves, the source of radio waves will be in a high frequency electrical circuit. So even though I'm saying these are the low frequency, this is really the highest frequency at which electrical circuits can operate. High frequencies that you can't keep the energy in the wires, it radiates away because of the electrons. Microwaves, these come from cell phones. Cell phones work around these wavelengths. Infrared, well, infrared radiation tends to come from warm objects. This is the night vision sort of systems. We're glowing in infrared radiation. Visible light, well, it's visible because we've evolved to see at these wavelengths because the sun gives off these wavelengths. Ultraviolet light comes from very hot objects. The sun does give off some ultraviolet light, but very hot stars, for example, give off a lot of UV. Now, I've asked you to put the asterisks. This is actually question 21. We'll do 21 at the same time, I guess. 21 says, add an asterisk by the ionizing radiation. So it was actually Einstein showed that the light comes in discrete packets called photons. So this is a higher energy photon. These low energy, this is high energy. A photon of ultraviolet light has enough energy to ionize the atoms and the molecules. So these are sort of dangerous. It's bad for your health, these things. These are dangerous because these have enough energy to break apart the bonds in your DNA and give you a burn. Infrared radiation, doesn't have enough energy to break the bonds. Sure, you could be cooked by it, but you just get hot. These radiations can actually break and cause damage on a molecular level. X-rays, okay, they're ionizing as are gamma rays. So X-rays we've talked about before. In the lecture I mentioned this. You can get electrons, accelerate them and smash them into a lead Pb nucleus, right? So when you smash them into a lead nucleus, they undergo a rapid deceleration, give off an X-rays. Gamma rays, these come from radioactive decay, so it's only in the nucleus of an atom do we have enough energy to produce gamma rays, okay? There are astronomical sources for these two, but I don't want to get into that right now. Okay, we did question 21, so let's skip to question 22. What did Heinrich Hertz demonstrate in the latter part of the 19th century? Hertz was the first guy to sort of transmit a signal using radio. He basically had a coil on one side of his lab. On the opposite side, he had a coil where it was connected to a spark gap, and it was very close to breaking down the air. And when he sort of sparked one on one side, it sent a signal. It produced a voltage in the coil, which was enough to cause the gap to break down and spark. So he produced a spark on one side, and then the other apparatus would produce a spark. So he actually transmitted a signal and received it. So in a way, Heinrich Hertz was the first to send a signal using electromagnetic radiation. I guess you could argue that if I switch a flashlight on and off, I'm doing the same thing, but you know what I mean. Who was, I can't say that, Guglielmo. Who was Marconi? Let's just go with Marconi. Who was Marconi? An Italian is an insufficient answer. Well, he was an Italian indeed, and he was sort of credited with the first person sort of to build a working radio. He actually transmitted a signal from sort of England down in Cornwall to Newfoundland. If you're ever in Newfoundland, there's a famous place you can go. I think it's called what's it called? Anyway, somewhere in Newfoundland you can go to a rock and there's a big plaque commemorating this event a long time ago where Marconi actually sent a signal across the Atlantic. Interestingly, of course, Tesla is also credited, and so I think in the end, Marconi is credited with inventing the radio. This can arguably be attributed to Tesla, and I think Tesla actually won the right in patent court, but this was at a much later date. Okay, in a way, Marconi was a guy who made a practical working radio. Tesla came up with the idea, though. 24. The wavelengths of radio and TV signals longer or shorter than those detectable by the human eye. The wavelength of visible light is tiny compared with these wavelengths, right? So visible light, very, very high frequency, very, very short wavelength. So no doubt about it, they are much, much shorter. Okay. 25. Wavelengths are longer. Wavelengths of radio and television are longer, right? Okay. 25. Can radio waves have the same frequency as sound? Well, yes, but those frequencies would be incredibly long wavelength radio waves. I don't even know what they would be. So yes, no reason why not, but there would be some very long wavelength radio waves. When you connect two loudspeakers to the output of a stereo amplifier, should you be sure the lead-in wires are of equal length to avoid a time lag between the speakers? Well, we know that the electrical signals propagate down wires close to the speed of light. You know, if I have one lead longer than the other, is that going to cause the speakers to be out of sync? No, it's not. Let's say we have 3 meters, right? So for a path difference of 3 meters, the difference in time travel, well, the speed of light is 3 times 10 to the 8 meters per second. So that's about 10 to the minus 8 seconds, right? So for an extra 3 meters, the signal takes 10 to the minus 8 seconds to arrive. The highest frequency we can hear is about 20 kilohertz, and so that has a period, right, 1 over the frequency, about 5 times 10 to the minus 5 seconds. So we can see that this number here, 10 to the minus 8, is much, much smaller than this number here, and so, you know, to actually have an effect, we would have to have the actual wavelengths shifted, and you can see this is a tiny effect compared with the period of the highest frequency you can hear. So it wouldn't be an issue. 27. If a radio transmitter has a vertical antenna, should a receiver's antenna, rod type, be vertical or horizontal to obtain best reception? Or if it's a vertical antenna, the wave is polarized in the vertical plane, hence I would need to have my antenna in a vertical direction. I just want to remind you that with this spreadsheet, we do have this thing I gave you here, which was from Scientific American a few years back. But you can see here's an antenna, and you can see this wave coming in. It's aligned in the same direction. So radio waves are polarized. There is something called circular polarization, which gets over this problem, but I'm not going to talk about that here. Sketch antennas that show the electrical part of an EM wave and the magnetic part. I didn't really do with the sketch, did I? Okay, let me make a note to myself to fix that. Sketch, sorry. The answer is really 28, question 28. Let's have a look at that worksheet again. This is really the answer. The coil of wire detects the magnetic field, whereas the rod like this would detect the electrical field, right? So just imagine we had the experiment where we had a magnetic field, we pushed a magnet through a Gilly coil that produced a voltage. The magnetic part of the electromagnetic wave goes through this loop of wire and produces a voltage, right? So the loop of wire detects the magnetic part, whereas the horizontal bar, that detects the electrical part of the signal. Draw a circuit diagram for a simple radio. This is from the overhead, I believe. but we have the antenna, right? The electric wave causes the electrons to slosh backwards and forwards. This circuit is magnetically linked to this, and it's sensitive to only one frequency. It resonates at one frequency, so this is just sensitive to one of the many frequencies here. That is then picked up, amplified, and off to the demodulator and the amplifier. Then explain the difference between AM and FM modulation. What are the advantages of AM? In AM, we encode the information on the carrier wave by changing the amplitude. In FM, we change the frequency to encode the information. FM carries more information, better sound quality, and it's less susceptible to interference. And again, interference usually changes the wave amplitude, not the frequency. A lost person may signal by switching a flashlight on and off using Morse code. This is actually a modulated electromagnetic wave. Is it AM or FM? Well, I'm modulating the frequency, the amplitude, aren't I? I'm not changing the frequency of light, I'm modulating the amplitude. It's pretty drastic modulation, admittedly, by switching it on and off, but it's modulation. So that would be an AM kind of way to transmit the information. Okay? 32, I think I've mentioned this a few times already. Explain why there is an upper frequency limit for electrical circuits. The reason is at high frequencies, the electrons in the wire get sloshed backwards and forwards very rapidly. They undergo rapid accelerations, and this rapid acceleration causes the energy to radiate away. So basically, there's an upper limit for electrical circuits because you can't send the high frequencies down wires anymore. Okay, make sure you watch the home viewing. As I said, part of it was the assigned viewing. Damn interesting article, was good to read. Two antennas met on a roof, fell in love, and got married. The ceremony wasn't much, but the reception was excellent. Good one. Okay, I think that's the end of this worksheet. Hopefully this format works. Works for you, let me know, give me any feedback. Okay, I'll sign off there.